Hello everyone, welcome to the channel Understanding.Concepts.Of.Physics. Today we are with finding out the kinetic energy of a rotating body. So subscribe the channel in case you have not done so yet. We'll be posting videos on all the topics of physics as and when. Every day a video is promised. Let's see how much we can do. Now kinetic energy of a rotating body, if you want to find out, then first of all we need a rigid body. So how I've drawn this diagram is, I have taken a rigid body, any shape, any irregular shape, and then drill machine, using a drill machine we are going to make a hole of that body and we'll pass a rod inside the body. So this is where the point where the hole is, and we have passed a rod, and if we push it from here, it is going to rotate like this. It is going to rotate in such a manner, and this line will be called as the axis of rotation. Now this body is made up of many small particles. So let's say the particle ka mass is m1, m2, and last particle is mn. And if I draw from the axis of rotation to that particle, that is radius 1, that is radius 2, and that is radius 3 or radius n. And when it is moving in this manner, the velocity would be always tangential. So v1 is perpendicular to r1, v2 is perpendicular to r2, and vn is perpendicular to rn. And I am assuming here that the body is moving with a constant angular velocity omega. So this is the way how I have drawn this diagram, and let's just start to prove it, find out. First of all, what have I considered? I have considered a rigid body rotating about an axis. So there is a missing part here. Rotating about an axis with a constant angular velocity as shown in the above diagram. So as shown in the, this is moving with a constant angular velocity as shown in the above diagram. Then we are going to assume certain things like m1. What does m1, m2 and mn be the masses of each particle? v1, v2, v3 till vn be the velocities, and r1, r2, r3 till rn be the radii, and e1, e2 and e3 till en be the kinetic energies. Omega is the constant angular velocity. So this is something we have written already. Now we'll start with the proof. So let's say we know that this formula for circular motion, that v is equal to r omega. So if this is that value formula, then I can just use as v1 would be equal to r1 omega, because the first particle's velocity is v1 and first radius is r1, but the angular velocity for each particle will remain constant, because if this particle moves 360 degrees, this particle will also move with 360 degrees, and other particles will also move 360 degrees in a fixed amount of time. So omega is a constant, that's why I am writing as v1 is equal to r1 omega, v2 is equal to r2 omega, and if you keep on going like that, you will get vn is equal to rn omega. Then we also know that the translational kinetic energy. Now translational kinetic energy is basically your linear kinetic energy, which is half mv square. This is our general formula. So with this formula, I am going to write the kinetic energies of each and every particle. So the first particle's kinetic energy would be E1, which is half of m1 v1 square. But v1 ka value we have found out in the above equation, that is v1 is equal to r1 omega. So wherever there is a v1, I'll put r1 omega. So r1 omega, but because there is a square, this will be square. Note this step, half of m1 r1 square omega square. Now if you do that for the second particle, this E2 would be equal to half of m2 v2 square, and this would become half of m2 r2 square omega square, because v2 ka value is substituted from the previous equation. And if we keep on going, I'll get En, that is the energy of the nth particle, that would be half of mn vn square, which will give me half of mn rn square omega square. So vn is rn into omega. Now because we want the total rotational kinetic energy, I'll have to add all this stuff. So my total kinetic energy would be equal to, rotational kinetic energy would be equal to E1 plus E2 plus E3 till En. So we have just added up. Now I'll put all the values of whatever E1 and E2 and E3 till En I have got in the above equations. So E1 is half of m1 r1 square omega square, and E2 would be half of m2 r2 square omega square, and the last particle would be half of mn rn square omega square. Now if you see all these terms, you will see that half is common in each of them, and even the omega square is there in each of the term. So omega square is taken out common outside, and half is also taken out common outside. Inside the bracket, what remains is m1 r1 square plus m2 r2 square till mn r square. Now if you just analyze this term which is inside the bracket, which I am underlining, is the sum of some similar terms. This is the sum means addition and sum means few, and it is similar terms. We can see mr square, and this can be written as summation sign. So summation sign is written somewhat like this, and half will remain as it is, omega square as it is, and this bracketed term will be written as summation mi ri square. Now how do we write this? Summation, whose sum is it? mr square, and the value, the initial value starts from 1. So initial value starts from 1, goes till n. So I equal to 1 to n. Whose value are these? This is values of i's, that is m's and r's. So whatever that bracketed term is there, I can just write summation I equal to 1 to n mi ri square. So you can just see how I have written this, and now this term, this entire term, if you compare, if this is your rotational kinetic energy, but you know that your translational kinetic energy is half of mv square. Now if you compare these two equations, this one is kinetic energy, this one is also kinetic energy, but this is in translational motion and this is in rotational motion. Half is compared with half, linear velocity is compared with angular velocity. There is a square here, there is a square here. That means whatever the bracketed term here is will be getting compared to this bracketed term, that is m is getting compared to this term. Now because m brings in inertia in linear motion, this term will bring rotational inertia in rotational motion. So this term will be called as rotational inertia. I'll just show you how it works. Because summation I equal to 1 to n mi ri square in rotational motion is similar to m in translational motion. See, if you see the equation, this term in rotational motion is similar to m in translational motion. Because m provides inertia in translational motion, this term summation I equal to 1 to n mi ri square provides rotational inertia in rotational motion. So this is the two statements which we need to add it up. Now what we are going to do is, we are going to call this term as I, as moment of inertia, or we also call as rotational inertia. So summation I equal to 1 to n mi ri square is called as moment of inertia or rotational inertia. So if I put this summation ke jagah pe, if I put I, so I'll have a I over here. In place of this, I'll have a I. So I'll get E rotational is equal to half of I omega square. E rotational is equal to half of I omega square. This is what the rotational kinetic energy is. Hope you have understood the video, and in case if you haven't understood any part of the video, you can just go back and listen it again. And if you have any doubts, you can comment on the section, and subscribe the channel in case you have not done so yet, and keep watching the videos. Every day you will be learning something or the other. Thank you so much. Have a nice day. Bye.